Okay, so applications of backpropagation. First, by understanding backpropagation, we can understand one of the most terrible problems of deep learning before it was working well. So here I have only 4 layers. It's a multi-layer perceptron with 4 layers. And as you can see here, it's for all the examples in my training set, we are computing some statistics. So the statistics of the activation values and over, let's say, 1 neuron. And here what we can see is that in layer 4, the average of all the activation function values of all the examples is close to 0. It's the output of the sigmoid which is close to 0, which means that I'm receiving representations that are very negative, that are smaller than -6. And if I take the derivative of the sigmoid evaluated at -6, the derivative is almost 0. It means that if I change a little bit the input of the sigmoid when the activation function is -6, it doesn't change much the output because of this non-linearity. So it's like by initializing badly my model, the gradient is 0, and I have no feedback on how I can change my parameter to decrease the loss, because I'm in a saturating mode. I should be in this region to have a non-zero gradient that will provide me a direction to improve the result. But since I'm here, the gradient is 0. And since to compute the gradient of the previous modules with respect to this module, the other modules were receiving only 0 gradient. So they were not being updated. So for 100 epochs, after seeing the dataset 100 times, the representation are changing very slowly. There is nothing really happening in the learning. In terms of the learning curve, it will be very flat. And it's because the sigmoid is really killing the signal, the feedback signal, at the output of the model, and the representation of the modules before cannot be updated, cannot be modified in order to minimize the loss. And after a while, because it's not a pure 0 feedback, it's a very, very, very tiny feedback, the first layer will begin to change a little bit the representation. The sigmoid at the output of the model will receive values that will go more and more to 0. And at this point, the signal will be greater than 0, and the backpropagation will work well. And the way to solve this problem of not able to backpropagate the signal is the initialization of these modules. So when you create a new module, be careful that the gradient that will be computed across your module will not be killed, that you will not have this kind of problem. And choosing the initialization is something that you must do. If you're creating a new module, you cannot let the library to choose the initialization for you. Okay, we can also do something else, something funny, called adversarial example. So remember in my example, I was taking the gradient of the loss with respect to all the parameters, but instead of stopping the backpropagation algorithm at this module, I computed the gradient of the loss with respect to the image. So it will give me the information that if I change this pixel, will my loss increase or not? And I will have the information for all the pixels in my image. And what some researcher at Mila did was to compute the gradient of the loss for a panda with respect to this image, and they retrieved this gradient with the same shape as the image. They will scale it down. They will multiply by 0.007 so that we won't see the difference as a human. And I'm really engineering some noise that I know that all the pixels with these values will change the loss a lot, because all the values for these pixels are The losses are very sensitive to this because it has been computed with the backpropagation. So I will combine these two. I will obtain this image, which for us is the same. Here I had 57.7% of certainty that it was a panda. This is the prediction of my model. By adding this noise that has been very well engineered by backpropagation, if I give this image to the model, now it predicts 99.3% of confidence that it's a gibbon. And a gibbon is a monkey like this. So backpropagation can be used to find the pixels where the model is very sensitive. If I change these pixels in the image, the loss will change a lot. Instead of hiding the noise in the image, what I can do is just to modify completely the image. And what they did here is to take a neuron very close to the output of the model, close to the DLE output, and they were computing the gradient with respect to the image. So all these pixels, the way I will modify the image will maximize the probability of having a DLE in the image. And they will do it iteratively. So first I took one image, I do forward, I choose the neuron of a DLE associated to the probability of a DLE, I do the backpropagation algorithm, I retrieve a gradient in the image space, I change my image, and I do it several times. So I will move in the image space, and I will find a picture that will maximize the probability of a DLE. And this one is clearly not an image of a DLE, but in some way, because I'm using modules that have properties like invariance to translation, invariance to scale, this is what will really maximize the probability of this neuron, the activation of this neuron. And it's something that is very fascinating. We don't understand why we have this structure in this image that will maximize the activation of this neuron. And to do so, we use backpropagation to navigate in the image space. Also, people are using backpropagation to compute saliency map. So I can find, again, the pixels where that they are the most sensitive, where the loss is the most sensitive to them. And what they did is to use some post-processing over the information of the gradient in the pixel image to do segmentation, to retrieve like an object in this image. And what you can do after that is, if I want to predict like if there is a DLE or not, and I use this technique, and the technique, I don't have my, and the technique returns me this image where I can only see the DLE. It means that the pixel where the model is sensitive with respect to the prediction are the pixels associated to the DLE. And now I have a little bit more interpretation on what are the features in the image that are used to predict my output. I'm not looking at inside the model because of the distributed representation. It's hard to interpret. I'm using backpropagation to find the pixels that are for which the loss is the most sensitive one. And there are now many different techniques for computing saliency map, but there's still a lot of research to understand. There are like, I think, 8 different techniques that are very popular, and there are a lot of research to really see, is it the right thing to do to interpret if the model is doing the right thing or not? And now for some techniques using backpropagation compute the saliency map, we can see that they are not giving interpretation at all. And we need more work to understand really what are the features that are used by the model. So the take-home message is that we can use linear approximation of a function represented as a computational graph. We see that linear approximation will give us the information that if I move a parameter, how the output will move, and we can do it on graph structure. Backpropagation is an efficient way to implement how to compute this linear approximation, and it works as a forward pass and a backward pass over the computational graph. And if you want to go more in the details, more in the math, I recommend you to read these links. And yeah, that's it. Thank you very much.